Okay, before we get into the next set of hypothesis tests, which are going to be tests on the population proportion, let me just summarize that last test that we just did because it was a two-tailed test. So, like I did with the left and the right-tailed test, I shaded where the p-value will be. So for a two-tailed test, the p-value is the combined area in the two tails. So the mean's in the middle, and then you have your test statistic, and then remember I said imagine we fold the paper in half and we line up the test statistic. One's gonna be positive, one's gonna be negative, and we have to look at the area in both tails. So you would combine the area in both the two shaded tails, and the two tails are equal in terms of area. So that's how we get the p-value for a two-tailed test. All right, so let's test the population proportion now. So instead of testing mu, the mean, now we're going to test the proportion, p. So the steps are exactly the same. The first step, why does it keep doing that? There we go. The first step is to still state the null and the alternative hypotheses and set your significance level alpha. But now, since we're going to be working with P, the population proportion, that's going to follow a normal distribution. So we're going to assume, like we did in chapter 8, chapter 9, that when we're looking at the sampling distribution of P hat, that we are going to satisfy the central limit theorem. So remember, n times P had to be greater than 10, and n times 1 minus P had to be greater than 10. So I'll guarantee you right now that anytime I give you a question involving proportions, this is going to be satisfied. So you don't have to check it every time. So we're going to assume that P hat follows a normal distribution. And remember, when we're working with the normal distribution, when we want to see how far away, right, our data value is from the mean, we calculate a z-score. So we'll be using normal z-scores when we test the population proportion. And our test statistic will be z, not t anymore. And we're going to take our sample data, the p hat, and we're going to minus the mean of all the p hats, which is mu sub p hat, and then we divide by sigma sub p hat. And remember, just a quick reminder, sigma sub p hat is equal to the square root of p times 1 minus p over n. So I taught you that in chapter 8. So we're going to use the normal distribution, and we're going to find the p-value. And just like we did in the other test, step 3 is find the p-value. 4 is the decision rule. Remember, if the p-value is less than alpha, we reject the null. And then step 5 is to state our conclusion in the context of the application. So same 5 steps. It's just now we're going to be working with the normal distribution, not the t distribution. And we're testing proportions. But I still have a template set up for you guys for proportions. And this is a normal distribution here. Okay, so let's look at an example. Let's do example 10. Some people are concerned that new tougher standards and high stakes examinations may drive up the high school dropout rate. The National Center for Education Statistics reported that the high school dropout rate for the year 2013 was 7.9%. One school district on Long Island, whose dropout rate has always been very close to the national average, reports that 157 of their 1,782 students dropped out last year. Is their experience enough evidence that the dropout rate is increasing? Test at an alpha level of 5%. So I'm asking you to conduct a hypothesis test. I want to know if there's enough evidence to support that the dropout rate is increasing, and I'm telling you to test at an alpha level of 5%. First step, always to formulate the hypotheses. But you have to realize now we're testing the population proportion. We're not testing means. How do I know that? First of all, there's no mention about a mean here. We're not studying the mean of anything. What we're studying is, look at what I told you, that we're investigating high school dropout rates. Rate is a percent or a proportion. The National Center for Education Statistics reported that the high school dropout rate for the 2013 year was 7.9%. That 7.9% is a proportion. Remember, a proportion is just a percent or a decimal or a fraction. That's the indication to me right now that I'm working with proportions. I was given a proportion, right, in percent form. So one school on Long Island, whose dropout rate has always been very close to the national average, says that 157 of their 1,780 students dropped out last year. So is this evidence that the dropout rate is increasing? So what are we testing here? We're testing that the rate, the proportion is going up, is increasing, right? Well, up from what? So what's my null hypothesis? What's the assumption about the dropout rate? What are we assuming to be true? Well, we're assuming that P, right, because P stands for our population proportion, is equal to 7.9%, or as a decimal, we write 0.079. We like to write it as a decimal because we're going to have to plug it in to different parts of the problem or like in the calculator sometimes. So just write it as a decimal. So P is assumed to be 0.079. But the alternative, the suspicion, is that this rate is increasing so that P is actually greater than, right, or increasing from 0.079. So since it's greater than, let's just make a note that this is a right-tailed test. And we're going to test at an alpha level of 5% or 0.05. So I'm going to state that too. So now we have to model the sampling distribution of the proportion. But before we get to the picture of the model, let's summarize the data that we collected. So we took a sample of 1,782 students, and out of the 1,782, 157 dropped out. So this larger number is the sample size, right? N is equal to 1,782. And the number that dropped out, or the number of observations, right, that dropped out, which is X, is 157. So let's write that down over here. So N, my sample size, is 1,782 students, and X equals 157 dropped out. So why don't we calculate the sample proportion P hat, right? So what percent of our sample dropped out? So let's calculate P hat. And remember, P hat is equal to X over N. So P hat in this case is going to be 157 divided by 1782. So let's plug that in the calculator. So take 157 divided by 1782. Let's go 3 places. So we get about 0.088, which is like 8.8%. That is higher than 7.9%. But remember, we can't just end the test now and be like, yep, we won. That's enough evidence. The dropout rate's increasing because I took one sample and the dropout rate is higher. It doesn't work like that. That could have just been a fluke or just due to chance. We need to use probability and look at the p-value to see how likely it is that we're getting these results just due to chance. So let's model the sampling distribution of the proportion. So we said it's going to follow a normal distribution. Here's my normal curve. Mu sub p hat. So let's do a quick reminder. I'll do this on the whiteboard. So just a reminder, this goes back to chapter 8. Mu sub p hat is equal to p, and sigma sub p hat is equal to the square root of p times 1 minus p over n. And if I want to get the z-score for p hat, I take p hat, I subtract all the means of p hat, the mean of all the p hats, and we divide by the standard error of all the p hats. So this is why chapter 8, sampling distributions, is so important, because we can't do all of this unless we're aware of the properties of these sampling distributions and we know how to model them. So mu sub p hat, so let's label our picture now. So mu sub p hat, which is the center of this distribution, is equal to p. And we're assuming p is equal to 0.079 unless we could prove otherwise. And now let's get sigma sub p hat. So that's going to be the square root of p, which is 0.079, times 1 minus p, 1 minus 0.079, over n, which is 1782. So you guys could plug that in the calculator with me. So we're taking the square root of 0.079 times 1 minus 0.079 divided by 1782. And I'm getting 0.0064 for my standard error. So now where within this normal distribution does our p hat live? This 0.088. I know it's bigger, right, than the mean. 0.088 is bigger than 0.079. So let's put it on the picture. So let's put it to the right of 0.079. So let's say that this is p hat right here, and that's equal to 0.088. Now, how far away is it in terms of standard deviations, right? What's the z-score? What's the test statistic? So it's the same process that we were doing with means, except now these are proportions. And we're using the z distribution instead of the t. But we still get the test statistic the same way. So to get z, take our data value minus the mean, divide it by the standard deviation. So we're going to take 0.088 minus the mean of 0.079 and divide by the standard deviation of 0.0064. So you guys could calculate that with me. And I got 1.41. So my z-score, which I also want you to label on the curve, is 1.41. So that means that this p hat is 1.41 standard deviations above the mean. And I'll put my z-score in blue. Now we need the p-value, right? Next step is to always get the p-value. And we already talked about a right-tailed test, right? So whenever we have a right-tailed test, the p-value is the area to the right of the test statistic, which I just shaded in green. So this is going to be my p-value. Now, I want you to think about how you're going to get that p-value. So how are we going to get that p-value if this is a normal distribution and the p-value is just that area under the curve? Think about it. If you said normal CDF, you're right, right? We started doing this back in chapter 7 with the normal distribution, normal CDF, right? The lower is going to be, we could use the z-score. Use the z-score for lower. It's going to be 1.41. The upper, since we're shading to the right, is going to be E99. But remember, you need the mean and the standard deviation. If you're going to use the z-score, the mean is 0, the standard deviation is 1. You could use the raw score of 0.088, but then you have to use the mean and the standard deviation of this distribution. I'm just going to use the z-score. So let's go to normal CDF. So second VAERS, and remember it's option 2. The lower is the z-score of 1.41. The upper was positive E99. And since I'm using the z-score, the mean is 0 and the standard deviation is 1. And we get a p-value of 0.0793. So my p-value is 0.0793. Remember, we always hope for a really small p-value so we can reject the null. But it has to be, in order to reject the null hypothesis, lower than the significance level alpha. And it didn't come in quite low enough, right? So what's my decision rule? We only reject the null hypothesis if the p-value is less than alpha. It's the same for any type of test. This rule will never change. So is the 0.0793 less than my alpha level of 0.05, right? Because look up here, my alpha is 0.05. It's not though, right? 0.0793 is not less than 0.05. So since the p-value is greater than alpha, we don't reject the null hypothesis, right? But we say we fail to reject the null hypothesis. So in other words, we don't have enough evidence to go with the alternative. So to put it in the context of this question, is there enough evidence that the dropout rate has went up, that it's increasing, that it's greater than 0.079? No, because we didn't reject the null hypothesis to go with the alternative. So no, there is not enough evidence to support the claim that the dropout rate is increasing. So no, there is not enough evidence to support the claim that the dropout rate is increasing. We didn't have enough evidence to reject the null hypothesis.